We had a pretty good discussion that focused on three main topics: planetary protection, uh, ConOps, concepts of operations, and technology development. We weren't kind of actively working in this sheet as we were talking. Alex was taking really good notes in a Word document that I've used to kind of populate this after the fact. But this is something that if people have comments that they want to go back and add afterwards, we can definitely do it. Okay, so from a planetary protection standpoint, we talked about the need to understand how we are forward contaminating Mars and what we can do to prevent it. There's kind of a general acknowledgement that we've already forward contaminated Mars with imperfectly or not at all sterilized spacecraft. And no matter where we go, we're going to have astronauts with leaky spacesuits that are going to forward contaminate the surface. The question then becomes, to what extent is that acceptable, and what level of contamination are we willing to accept? And I think the answer to that is it's site dependent. So depending on where we want to land on Mars, the proximity to ice that could be turned into water, or changed thermal environment that could lead to subsurface or surface liquid water, that will determine the level of contamination we are willing to accept. But one thing we should do is think carefully about how we characterize how we're contaminating the surface. And so one thing that we discussed was investing in the technology to drive down the price of isotopically spiking spacesuit gases and water. So we have, I think Pascal mentioned, right now spacesuits leak something like a half a kilogram of water per hour. If we have a specific isotopic composition for that water, and then we collect samples, we should be able to identify the difference between volatiles coming from the astronaut spacesuits themselves, as well as volatiles that were inherent in the surface. And so this is something that has been requested, for instance, for Eclipse missions, but has been determined to be really expensive and not a big priority. And so thinking about how we could invest in technology that would drive down the price of this process, so that we could really understand both at the moon, where we're interested in sampling volatiles, and on Mars, where we're interested in understanding forward contamination for planetary protection purposes. How can we drive down the price of this? Or is there another way that's less expensive that we can monitor contamination due to human exploration? So that was one topic that generated a lot of discussion. In terms of technology development, we talked a lot about understanding how we will high grade samples on Mars and testing those processes at Artemis Base Camp. I think there's a general acknowledgement that field geology and using astronaut and crew and backroom expertise is going to be the main tool to high grade samples at the moon. But there might be more detailed spectroscopic or isotopic or other types of tools we'll want to use at Mars to figure out which rocks or soils we want to bring home. The crew will likely collect way more samples on Mars than we'll be able to bring back. And so we'll want to have detailed processes and for high grading samples, and we'll really want to understand what technology needs to be developed and prioritize for Mars to bring back the best samples. For Mars exploration, working on the assumption that finding extant life is going to be a main priority, we will need to either drill deep or explore caves. So the surface of Mars is unlikely to support extant life. We might find microbial fossils, but we will have to access the subsurface for any shot at finding extant life on Mars. And so drilling deep, it could also be a priority for instance, sampling volatiles at Artemis Base Camp on the moon. And so our main priorities would be to develop tools that will allow us to access the subsurface, either through deep drilling access or cave exploration. We spent a lot of time also talking about communications infrastructure and making sure that astronauts and ground crew are communicating in an effective way. This is something that the Artemis 3 geology team and the NASA science team are already kind of working on. But of course, Artemis communications are going to be quite different from communications with the crew on Mars. And so there are certainly tests that we could perform on Mars, including long latency communication on the moon that will be in operation on Mars. And this is not something that we would likely do in the first few Artemis missions. But as Artemis Base Camp is established and crew become more independent and learn how to work in the lunar environment, testing the communications infrastructure, the communications practices that will be most likely for Mars is something that we should do at the moon. Related to some of the other processes that we talked about in terms of sampling and exploration of the subsurface, one thing that we can certainly test on the moon and work towards on the moon is understanding the best way to evaluate human robotic interactions and robotic assistance in prospecting and collecting data to help astronauts identify and prioritize areas of interest. The risk is that robots slow down humans, or that they provide so much information that they kind of overwhelm the astronauts. And so it's really incumbent upon the crew and the ground crew support to find that balance of human-robot interaction that provides the most optimized exploration strategy without overwhelming or bogging down the crew. This is something that can definitely be tested at base camp. And then finally, we had a short discussion about understanding resource and energy consumption at Artemis Base Camp. This is something that we should be very carefully monitoring and understanding, and we should at the same time be developing models for how the information that we gain about energy and resource consumption at Artemis Base Camp will feed forward and translate to Mars exploration. There are certainly variables on Mars that are going to be different in terms of what resources are available and which resources are consumed at what rates. But we should be thinking now, or at least thinking during Artemis Base Camp operations, about how the information that we gain related to resource and energy consumption will feed forward to Mars. So I'll skip straight to the white papers. So we had 2 volunteers to lead white papers related to sample high grading and technology development. Jorge Nunez has agreed to lead a white paper related to that. And Pascal Lee has agreed to lead a white paper related to deep drilling or cave exploration, or more broadly, technology development for access to the subsurface. So that was the bulk of our discussion. I think I hit all the main points there. I will share this Google Sheet in the chat, and I'm happy to take any questions if there are any.